Hello everyone. So let us see the third problem from weekly contest 336, that is count the number of beautiful subarrays. You are given a zero indexed integer array nums. In one operation you can choose two different indices. Choose a non-negative integer k such that the kth bit in the binary representation of nums of I and nums of j is 1. Subtract 2 to the power k from nums of I and nums of j. Subarray is beautiful if it is possible to make all of its element equal to 0 after applying the above operation any number of time. Return the number of beautiful subarrays. Okay. So let's say we have a subarray P1 and 2. Okay. Now what is the binary representation? It's 1 1, it's 1 and it's 1 0. We have to choose two numbers and in them choose a integer k such that the kth bit is set, that is kth bit is 1. So let's choose 3 and 2. 3 and 2. What is the binary? 1 1 and 1 0. Let's choose k equals to 1. The kth bit, that is the first bit, is set. Okay. Now what can we do? We can subtract 2 to the power k from this and this, nums of I and nums of j, which is nothing but 2 to the power 1. Okay. So if we subtract 2 from 3 we get 1, and if we subtract 2 from 2 we get 0. Okay. So they have been transformed to 1 and 0. In binary it's 1 and it's binary it's 0. Okay. So this 3 has now turned to 1, this 1 remains as 1, this 2 has turned to 0. So this is what we are left with. So in binary it's 1 1 and 0. Now we can do our operation again. Okay. So if we choose these two numbers, okay, and if we choose k equals to 0, we can see that the 0th bit is set, isn't it? So we will subtract 2 to the power 0 from this and this. So what do they become? This becomes a 0, this becomes a 0. So ultimately in the whole subarray all the numbers have been transformed to a 0. So this is a beautiful subarray. Okay. Now let's say we only had this subarray 3 and 2. So we saw that after performing one operation this 3 becomes a 1 and this 2 becomes a 0, and there is nothing we can do further, right? We can't transform this 1 to a 0, isn't it? Because in order to transform, this is the 0th position, right? So in another number we will need a set bit at the 0th position, then only we can perform this 2 power k operation, isn't it? So if we just ignore this 2 power k, what basically is being said that if we have a number in which the ith bit is set, or say kth bit is set, and in the another number the ith bit is same position bit is set, we can transform it to a 0. Okay. We can transform it to a 0. Okay. And say after transforming this is what remains. Okay. Let's say this and in this one say this. Okay. Now in this one this position and this position are not same, right? So in order to turn this one to a 0 we will need another number in our subarray in which in the same position we have a set bit. Okay. Let's say this is another number. Okay. So this position and this position has a set bit, so we can use these pairs and we can turn them to a 0. Similarly, in order to turn this position to a 0 we will need another number in which the same position has a set bit. Okay. So these two will pair up and turn themselves to a 0. Now what does this 2 power k operation actually mean? Let's say our number is 4. Okay. In binary it's 1 0 0. Now this position is 0th position, this is the first position, this is the 2th position. Okay. So if you choose 2 power 2 which is 4, and if we subtract 4 minus 4 we get a 0, right? That's what we are doing. That's what this 2 power k operation means, basically turning that set bit in that particular position to a 0. Okay. Now our task is to know that if all the numbers in the subarray can be turned to a 0 or not after that many operations. Okay. Let's say the numbers in our subarray is 1 2 and 3. Okay. This is 1, this is 1 0 and this is 1 1. If we put the binary representations on top of each other we get something like this, right? We use this 0th bit and 0th bit to turn themselves to a 0 by doing 2 power 0 minus 2 power 0, and this first bit by subtracting 2 power 1. Okay. Now if we see how can we turn this to a 0, we have 1 and 1 here, right? How can we, what operation can we do so that this becomes a 0? We can do a XOR operation, isn't it? So 1 XOR 1 is 0 and 1 XOR 1 is again 0. That means if we do 1 XOR 2 XOR 3, we get a 0. That means this subarray is beautiful if the XOR of all the numbers in that subarray is 0, isn't it? This is one observation. Let us say we have this array, given array 4 3 1 2 4, 4 3 1 2 and 4. But in binary representation, this is 1 0 0, this is 1 1 1 1 0 and 1 0 0. Now what did we do? In the subarray, we XORed all of them, right? All the elements. So let us do a XOR on all of them, okay? So initially our XOR is 0. Then we do a XOR, we get 1 0 0. Then we do a XOR, we get 1 1 1. Then we do a XOR, we get 1 1 0, right? This and this, they XOR up and become a 0. Now we do a XOR 1 0 0. Now this 100 and 100, okay, they XOR and they become a 0. Now we have this in our hand. Can we observe something from this? Initially our XOR was 0, and after XORing all the elements in the subarray, in the whole array, we got again a 0. What does that mean? If we consider this whole array, it is itself a subarray, right? So if the XOR of all the elements in the given array is 0, that means the array itself is beautiful. Fine. One more thing to observe is that here we have got 100, okay, as our prefix XOR. We are doing a prefix XOR, right? And we have got again 100. What does that mean? It means that when we had 100 in our hand, okay, and when we XORed all these elements in this range, we got a 0. That's the reason why we have got the same number again, because by the rule of XOR, a XOR 0 is a itself, isn't it? And a XOR a is 0. XOR of same elements is 0, right? So we had 100 here, okay, and after XORing up till here, this index, we have got the same number again. Then it definitely means it's guaranteed that this number was XORed with a 0. That's why we are getting the same number. So here is our observation. Say we have got a result A after doing XOR from 0 to our position, current position, okay, and after taking few more XOR at few more indexes, we have again got the same number, okay. This A has been achieved again. That means the distance, let's say we got a XOR at let's say this position, okay, and after traveling for say like few indexes, we got this same number. That means that the distance that we have traveled so far, okay, that gave us a XOR of 0. That's the reason that this A after XORing with this 0 gave us a A. I think we have a question in lead code already, like subarray sum divisible by k. It was something like if we get a reminder here say x, and we get the same remainder here say x, okay, then that means this subarray is divisible by our k, okay. So it's the same logic being applied here. I will repeat once more. If at an index I, let's say we are getting a, and after doing few XOR operations, prefix XORs at few indices, at again another position we get the same XOR result, then that means after this position I, this subarray gave us a XOR of 0. That's why we are getting the same number, because look at the rule, isn't it? So that is what our logic is. We are going to take prefix XOR, okay, and if we see that a XOR result has already been achieved in the past, then that means we had a good subarray, okay. Let's see how we are going to do that. 4 3 1 2 and 4. Initially our XOR is 0, okay. Here it's 1 0 0, XOR of 0, and this is 1 0 0, okay. Now we will see that in the past, have we achieved this same XOR result? No, we have not, okay. So we will move to the next. Before doing that, we will store this, that okay, this XOR result has been achieved one time. This is also a XOR result, right? Our XOR was 0, so we will store this one as well, okay. Now we go to here, our XOR result is 1 1 1, okay. In the past, have we achieved this same XOR result? No, we have not, okay. Now let's keep it in our record. Now let's come here. What is the prefix XOR? 1 1 0, okay. In the past, have we encountered this same XOR result? No, we have not. We have not. Okay, record it. We might encounter it again in the future. Okay, let's go. What is this XOR here? It's 100. Have we encountered this XOR result in the past? Yes, we have. We have. How many times? One time. That means we have one subarray that gives us a 0. That is in this range. Isn't it? In our answer, we can clearly see at the beginning we saw that 312 gives us XOR result of 0. Isn't it? So this is a subarray. So in our answer, we are going to add this one. Okay. And we will update this. Okay, fine. Now let's move up to this index. What is the XOR result here? It's 0. Isn't it? Now, is this XOR result previously achieved or not? Yes. Our XOR was initially 0 and we have got this same XOR again. Okay. This whole subarray is giving a XOR of 0. That means it itself is a subarray. Now, how many times did we get this? One time. So 1 plus 1. Increase its frequency. Okay. Let's say we had few more numbers. Let's say x, y, z. And let's say we again get a XOR of, let's say 100 here. Okay. Now, what would that mean? If we are here, okay, and we are getting a XOR of 100, which was already achieved 2 times in the past, what does that mean? It means that in this range, the XOR is 0. That's why 100 XOR 0 is giving us 100, not 100, 100. And in this position also, we have a 100 XOR, right? That means that in this range, the XOR is 0. That's the reason 100 XOR 0 is we are getting 100 again. So that's what it means. So in that case, we will add plus 2 because this is 2 more subarrays, isn't it? So that's how our algorithm is rolling. And what is this? This is a hash map. You can clearly see. Okay. So now let's discuss what we are going to do. We will create a prefix XOR array. Prefix XOR array. Okay. Then we will create a hash map. In it, we will initially put 0 and 1 because our XOR is initially 0, right? Now we will iterate over our prefix XOR array. Okay. Now if we see that our prefix XOR was initially achieved in the past. Okay. If it was achieved in the past, that means we have got a subarray. Then we have got a subarray which gives us a 0. This, then this. Okay. Clear? So how many times? Say x number of times. So we will add that x to our answer. Okay. So pretty simple. Let's see the code now. So this is our code. We record the length. Okay. We'll take a prefix array. Okay. We take long just for safety. Prefix of 0 is nums of 0, right? Because initially we have 0, right? And 0 XOR 4 is 4 only. So in the first position, we have the nums of 0 only, right? Just see here. Okay. In the first position, we have this number only, right? So after that, we start iterating. We create our prefix XOR. This is pretty simple. If you can take prefix sum, you can take prefix XOR also. It's just this operator. Okay. Now we take a hash map, okay, of long integer type. We initially put 0 and 1. Okay. Initially our XOR is 0. So we put a 0 and its count is 1 and answer as 0. Now we iterate over our prefix array. Okay. Now we will iterate over our prefix array. Okay. And we will see that if this XOR was encountered before, if it was encountered before, then in our answer, we will add how many times it was encountered. It's the same thing, right? We are recording the frequency. So we are adding the frequency, the number of times that XOR was encountered before. That number of times is nothing but the number of subarrays, right? See here, if we are here and it was encountered 2 times, right? This and this, this and this. That means from here to here and from here to here, we have a 0. So we add that frequency. Okay. And finally, when we have encountered this same XOR result again, we will update it. And at the end, we will return our answer. Okay. Now, instead of creating our prefix array, we can do the same thing right on the go. Okay. We can take a XOR variable. Okay. Initially to 0. And in our map, we put this mapping already 0 and 1. Okay. Now we start from 0. Then we do a XOR and see if this XOR is already present or not. If it is present, then in our answer, add how many times it is present. Okay. That how many times is nothing but the number of subarrays, isn't it? Then we update the frequency and then we move on. Okay. And at the end, we return our answer. So this is the solution. Okay, now if we talk about the time complexity, so in the previous solution we were using a prefix array and a hash map, right? So the time complexity would have been big O of 2n, which is nothing but big O of n only, right? But in this one we haven't used any prefix array, just the hash map. So our space complexity is big O of n, and our time complexity is simple big O of n. Okay, this is our time complexity. So this is all about this problem from my side. So if you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next one. Bye bye.